Okay, this video is about vector geometry, and this is something that comes up both at GCSE and at A level. So this is supposed to be slightly dual purpose, kind of aimed at somewhere in between the two, I guess. Anyway, worth just saying really what vectors are all about, because vectors come into other aspects, certainly at A level. And vectors are things basically that that they're values that have both size and direction. Size and direction, both important, and therefore we can describe things like velocities and forces by vectors, because the size of them and the direction in which they are acting are both important. Now, it's useful to represent vectors graphically by a line, and we can draw a line in a particular direction and give it a particular length to represent the sort of magnitude of the vector. So so two vectors, for instance, that have the same length and direction are then essentially the same, have the same value. Now, in this video, what we're interested in is vector geometry. So this is how we use vectors in order to solve geometric problems. So if you can imagine some geometric shape, like a triangle, we put arrow heads on the lines, then basically each line therefore has a magnitude, which is its length, and a direction, you know, which what the angle is, but of course now we put an arrow ahead on, we've got a direction as well. And so so basically we can assign a vector value to a line in a geometric shape, and that vector value, we could say the length and the direction. More typically we might describe it in terms of 3 along and 4 up, which implicitly is gives you the length and the direction. Okay, so so there's a few forms in which we will see vectors expressed. This is a column vector. When I say 3 along 4 up, that's what we're saying with this form. This is a polar form, which is, so this would be the magnitude, the actual length of the line, and this would be its orientation. Sometimes we measure it anti-clockwise from sort of rightward horizontal. Sometimes we do it as a bearing, so that would be clockwise from due north. Okay, so that's a possibility. We tend not to see this very much, certainly not at GCSE, and not so frequently at A level either, really. Now this is what you might call line segment form. It's basically indicating you know, a piece of our geometric shape, which will have a vector value. So this, with this arrow on top, is sort of indicating that. So we'll come to that in a while. Also, we often ascribe algebraic values to vectors, either because we don't know them and we're trying to, they're an unknown in some kind of equation, or more typically that they're actually, we are going to find our answer in terms of this algebraic value. So it wouldn't really matter what the value was, whether b was 3, 4 or 4, 7 or something like that. Then if we're expressing our solution in terms of b, then that's kind of the objective. The other form is something that we tend to see more in terms of forces and velocities, and at A level, again, not really a concept for GCSE, or not really a bit of notation. But 4J, where the I direction is sort of rightwards horizontally and the J direction is upwards vertically. Okay, so we'll see some of these as we go a bit further down this this page. We also come across the idea of a position vector. I mean, everything we can do with vectors, we can tend to do in sort of just in some space, where this, you know, the sizes are important, but it doesn't. We don't really have any sort of coordinate system. So the idea of a position vector really just allows us to put our geometric shapes onto some coordinates system. So what we're sort of saying with this is, if some point A has got a position vector 3, 4, then the vector OA, should have a line on the top there, is 3, 4. A has position vector 3, 4 means vector OA equals 3, 4. Or maybe some algebraic value, some letter. Okay, so that's it. So it's a bit of an abuse of terminology, really, because a position is a position. It's not a vector, really. But anyway, that's what it kind of means, and it means we can actually sort of define a coordinate system, and that can be useful in some problems. Okay, so let's just have a little bit of a kind of browse through some of these ideas then. So first of all, yeah, direction is important with a vector. So if I've got here's my line and my geometric shape. If I've got put an arrowhead on it there, and that's 5 along and 1 up, then that's what that would be. But of course, if I put my arrowhead at the other end, then it would be the negative of that, coming back in the opposite direction. And of course, as I say, this would have the same value because it's the same length and the same direction. So if we think, for instance, about a parallelogram, that would have corresponding parallel sides would have the same vector value. Okay. Vectors in a closed loop add to 0. Yes, so this is starting to become sort of quite important here. So if, for instance, we see this situation here, if we go 5 along, 1 up, then we go -2 along, means we're going backwards, obviously, to the left, and 3 up, we get up to this point. And then if we go 3 backwards and 3 downwards, and we get back to this point, which is our original point. Well, kind of makes sense, really, doesn't it? Because if you add up 5 and -2 and -3, you get 0. If you add up 1 and 3 and -4, you get 0. So your net effect is going to be 0, and that's going to be in a closed loop. They're going to add up to 0. But to look at it in a way which is actually quite useful for solving vector problems, if we can imagine these 2 black ones here, the net effect of this is the same as this green one here. So what have we done here? I've just reversed the arrow and the signs on here. So interesting thing is, if we know these black ones and we want to actually work out what the green one is, then what we can do is we can just add these 2 together, these 2 black ones together. So this is kind of quite interesting in vector geometry problems, because where we don't know the value of a vector, we can use some other route to get from our starting point to our end point. And if we know those, then it's going to give us the value of, in this case, the green one. And of course, there's just 2 involved here, but it might be more complicated than that. Okay, now we mentioned line segment form. So this is the same idea expressed in that notation. So PQ plus QR plus RP, that goes round in a closed loop, so that's equal to 0. And correspondingly, if we change the direction of this arrow from being RP to being PR, then we can say that PR is equal to PQ plus QR. Now, this is really, really useful bit of notation, because if we look at PQQR, what we get the idea really is this bit here, these Q's sort of, in a sense, they cancel out. So if we've got something like PR, we can expand it out. Might be another point here, B into PB plus BR. And this is something that's going to actually help us solving these problems. And so this line segment form here is going to be quite useful for sort of manipulating and kind of working out unknown vectors. Scalar multiples of a vector are parallel. Okay, so these vector values, so this one is twice as long in the same direction as this one, and it has twice the value. This one has half the value. So that's the other consequence, and that comes into virtually every problem. Now, I mentioned algebraic expressions. So we may not know the value of a vector, and we may not need to know it if we're expressing some answer in the form of unknown vectors. So yeah, so these two, these vectors, this vector might be A. So A, if in a two-dimensional space, A would be two values like 3 and 4. Which we could write as a column vector, let's say. It's usually emboldened, which doesn't is not too easy when you're doing handwriting, but these letters, usually small letters, very often A's and B's and C's and so on. So these two would be equal, and this one obviously would be the negative, so that would be minus A. Same idea here, where we've got the lengths. This one's twice as long as this, so that would be 2A if this one is A, and so on. And for instance, if we're thinking about sort of algebraic values here. So if we want the green one, if this is given to us as A, this one as B, then this is quite simply A plus B. So we'll see that in a moment. Okay. And then I just mention about position vectors. Yeah, see on all the diagrams above, I haven't got any axes on there. Because it doesn't matter where it is in space, because it's the relative position of the points that matters. But sometimes we want to fix this into some kind of coordinate system. We'd have some coordinate system here, which has got the same scale. So that being 5 along there would be 5 along here, so we're talking about the same scale. Okay, so if we just look at this example here, PR equals PQ plus QR. Yeah, we talked about that before. But here, if we're told that P has a position vector A, that means that OP is a vector value A. And if we're also told that PR is B and QR is C, find the value of OQ. There we go. Might say find the position vector of OQ. Then well, let's just write this out. OQ is equal to OP plus PQ. Look, I've done that expansion there. That sort of the P's would cancel, wouldn't they? So OP plus PQ. And PQ, well, we don't know what PQ is, but we've got PR and RQ. So PQ equals PR and RQ. So notice got the R's here on the inside. And RQ, well, we've got QR is C. So if we just change the sign on there, we're going to get OP plus PR minus QR, and that's going to be A plus B minus C. So vector OQ, or we might say the position vector of Q, would be vector value A plus B minus C, whatever those values are. Okay, so there's kind of some of the principles. Let's have a look at one or two examples. Right. Right, so what have we got here? OAB is a triangle. M is the midpoint of OA. That's there. And N is the midpoint of OB. Vector OM, or the vector value of OM, is M, and of ON is N. Show that AB is parallel to MN. AB parallel to MN. Now, as we've seen from above, the two vectors, two lines are going to be parallel if their vector values are scalar multiples of each other. We saw that with A and 2A, didn't we? Or half A and 2A. Before. And that's what we're trying to establish. So let's just work out what these vectors are. MN is equal to MO plus ON, expanding that out. Right, MO is minus OM, so that's going to be minus M. Yeah, OM is going that direction, it's M, but we're going to M to O, so that's minus M. And ON is N, straightforward. So that's equal to minus M plus N. Right, that is N minus M. And then AB. AB, what's this vector? AB. Well, again, expanding it in line segment form is going to be A O plus OB. Well, this is the midpoint. So vector MA is the same length and direction as OM, so therefore it must also be the vector value M. So OA would be 2M and AO would be minus 2M. AO minus 2M. And then OB, well, with similar argument here, this is another N here from N to B. So OB in totality would be 2N. So that's going to give us, for AB, that's going to give us 2 into N minus M. So MN and AB are scalar multiples of each other, and therefore they are parallel. Very common form of question. Right, I've just mentioned at this point that very often these vector questions come in two parts, a part A and a part B. Part A is usually pretty straightforward. Part B is a bit more complicated. But it's worth doing these questions just, just for part A. And, if you're a bit stuck for time or so on, I'd say, 3 or 4 marks that might be on offer for part A are well worth having a go at, even if you don't go on and do part B. Okay, so we'll have a look at this one. It's a bit more involved. ABC is a straight line. Yep, there we go. And AB to BC is 2 to 5. AB is to BC is 2 is to 5. Okay, so this AB is 2/7 of AC. Is another way of looking at that. OA equals 2A plus B. OB is 3A plus 2B. Whether or not this is the origin on some coordinate system doesn't really matter, does it? It's just a point on our diagram. But I suppose you could have been, this problem could have been expressed slightly differently. They could have said point A has position vector 2a plus b, point B has position vector 3a plus 2b, and find the position vector of C. Could have, in terms of A and B, that could have been the way that this problem might have been expressed. But anyway, they've not written it like that. They've written it like this. So let's have a look. OC, we want OC. So let's kind of work this through and find out how we, just think it through. OC, again, is our expansion, was OA plus AC. What is AC? Well, I already said it's 2/7 of AC. So AC, turn that round, AC is going to be 7/2 times AB. Now I've used AB because we know these two, or we know them in terms of A and B, which is all we need. So that's quite useful now, because we've actually expressed AC in a form that we've got a decent chance of working out, I think. So so we're going to expand AB. Well, AO plus OB, and now that's looking promising, isn't it? Because we know OA and we know OB. AO is, of course, minus OA. So we can rewrite this as OA plus 7/2 times minus OA plus OB. Right, okay, so we're just kind of expanding these things out and substituting as we go through. We can rewrite that if we group our OA's together, minus 5/2 OA plus 7/2 OB, which we could write as that if we factorize out the half. And now at this point, and just to add that, I think it's generally useful and good practice to actually work in this sort of line segment form really until, as late as possible, until you more or less have to actually substitute in your algebraic values, because it's easy to work with, basically. So if we substitute our OB and our OA in there, then we're going to get this. We collect like terms. Eventually we're just going to end up with this half into 11a plus 9b. So that would be this vector OC, or as I said before, we might say it is the position vector of C, if this were to be the sort of the origin. Okay, so that's quite a good example. So look at this one slightly different. Here are two vectors, AB 6 minus 9 and CB 1 3. So 1 along and 3 up. Find the magnitude of AC. Now, when we're talking about vectors, and I mentioned the polar form, we might describe it in terms of the length of the line and the angle. Could be the anti-clockwise from the horizontal, or it could be a bearing, which would be clockwise from due north, or really any other system that we wanted to set up. So that would be a way of describing or a vector value. Here they're just asking for the magnitude. Okay, in other words, the length of the line. The magnitude of AC is its length. Well, we might write it like that with these vertical lines there. That signifies the length of AC. So let's have a look. AC is equal to AB plus BC. That's just expanding that out. And BC, of course, is minus CB. We write it like that because we've actually got CB here. So if we work that out, just subtract one from the other, then we get this vector 5 minus 12. So this is the vector of AC. However, it's asking us for the magnitude, which is the length. So at this point, we're going to kind of rely on a bit of Pythagoras. So if we can draw this, we've got 5 along, 12 down. So what would this length be? Well, you could work this out with Pythagoras, and if you know your Pythagorean triples, you will know that 5, 12, 13 is are the lengths of a right angle triangle. So, in other words, this length here would be 13. Magnitude of AC equals 13. So we could go on and actually find the whole vector value. We've got the magnitude, we would just need the angle. If we were to do that as a bearing, then we'd, we use a bit of SOHCAHTOA on here in order to work out, well, this angle here between the line and the vertical, and then kind of turn that into a bearing, we'd find that it was 155.4 degrees to 1 decimal place. So that would be that would be the vector value if we chose to express it in that form. Okay, so that is quite an example, I think. Let's have a look at this. Right, OACB is a parallelogram. I mentioned parallelograms before, because the parallel sides will have the same vector values. So here we can see from this diagram, this value here is A, and this is B. So this means that this one is B and this one is A. Okay, so and it also says D is the point such that AC equals CD. So if this one is B here, then we know that CD is also B. Okay. What else have we got? So yeah, so that's it. And then we've got the point N that divides AB in the ratio 2 to 1. This being the 2, this being to the 1. So it's kind of two-thirds the way along from A to B. Write an expression for ON in terms of A and B. Okay, so yeah, here we go. And now ON equals OA plus AN. I kind of missed a step out here because AN, as I said, is 2/3 away along from A to B. So I've just written it as 2/3 AB. And then rewrite that as OA equals 2/3 of, well, again, here's our expansion, AO plus OB. And AO is going to be the negative of OA, so that will be minus A plus B. So A plus 2/3 minus A plus B. So that would be, if we group our A's together, that's going to be a third A plus 2/3 B, or which we could write as that if we factorize on 1/3 end. So that is ON. So that's a typical sort of 3-4 marker that it's pretty straightforward, really, to do that. Once you get the concept of vector geometry and how we expand and scale these things to 2/3 AB. If you can do that, then really it's as sort of straightforward 3 or 4 marks as you're going to see in any question, I think. Then he goes on to say, prove that OND is a straight line. OND is a straight line. So the important thing is that it's a straight line really if ON and ND are parallel because they share a point. So if they're parallel and they go through the same point, then they must be a straight line. It must be collinear, we would say. Okay, so OND is a straight line if ON and ND are parallel by scalar multiples. And in actual fact, ND, well, we could do that, but the same logic also applies to ON and OD. And OD is going to be pretty straightforward to do. Let's do that first. OD, expand out to OA plus AD. Well, OA is A, AC is B. And we know this is C is the midpoint of this, so CD is the same length and direction as AC, so therefore that must be B, and this must be B, so altogether AD is 2B. So that's what we've got here. OD is A plus 2B. And now we could go through the sort of argument and sort of say, well, OD is ON plus ND, therefore ON is OD minus ND. 2/3 of into A plus 2B. Anyway, we can see that that is a scalar multiple of that. So whether we use OD, that's this whole, or whether we use this bit of it, ON, they're obviously a scalar multiple, or ND, then they're a scalar multiple of this. So ON and ND are scalar multiples and share a point, so they must be collinear. Okay, so a word which seems to always be spelt wrong. I think it would have one L, but apparently we've got to put two L's in it. Right. Okay, so that's straightforward. And here is something on a fairly similar line, really. APB is a triangle. N is a point on AP, such that, well, it's marked on the diagram. A 2B, B there. That's okay. Right. So and right. So that's the first question, is to find the vector PB in terms of A and B. Okay. So PB, that's this here. Again, PB equals PA plus AB. There's our expansion. We know AP, don't we? So just twisted this round and negated it. So that's going to be, it's going to be minus 3B plus A minus 3B. PB equals A minus 3B. Again, maybe 3 marks for that. Okay, then it goes on. PB is the midpoint of AC. Okay, and M is the midpoint of PB. So that's a midpoint. That's a midpoint. Show that NMC is a straight line. So NMC is a straight line if NM and MC or NC, the same argument as the previous question, are parallel. And scalar multiples of each of that says IE, but basically if they're parallel and then they're scalar multiples of each other. Then so NM, let's expand that out, equals, well, we've got a double expansion here, NA plus AB plus BM, right? Because I'm looking at how are we going to do NM? Well, we basically, we don't know this, but if we can track along here, down this sort of circuitous route for getting from N to M, we certainly know that. B, we know that. We will know this. We will know this because this is half of BP, and we know that we can express BP in terms of AB and AP. So therefore NM is equal to NA plus AB from there, and then BM is half of BP, which of course is minus a half of PB. So if we rewrite this, and we get it in that form, right? Okay, I think we've come all the way now with our line segment notation. NA is minus 2B. It's going to just negating that, plus AB, which is A, minus a half of this thing we've already calculated in part A minus 3B. Then if we just have to collect like terms together, and we're going to get half into A minus B. And now if we look at NC, right, okay, it's very similar to the last problem in actual fact. It's NA plus AC, but we can easily see that's minus 2B plus A plus another A, minus 2B plus 2A is 2 into A minus B. So these two, NM and NC, are scalar multiples of each other. So they're parallel, and of course they have a point in common, which is M, and therefore that must be a straight line. Okay, so there's another example. Right, well, that's probably all we need to do at this stage. I say I urge you just to spend a bit of time with this, because say if at least you will be able to do the part A's and bag your 3 marks or your 4 marks or whatever. And there's a good chance with a bit of practice you'll be able to knock off any subsequent part B or whatever. All right, so hope that's been useful. Thanks for listening.